Hello and welcome to this webinar on cost-benefit analysis in SHM projects. This presentation was the opening keynote at the SHM E5 conference held in Cancun last December, and I thought it would be interesting to repeat the presentation in the form of a web seminar for those that didn't attend the conference itself. So today we will talk about cost and benefit in SHM projects. So I will speak about three concepts in particular: what is SHM and how to calculate the cost, and how to find benefits that can be shared and communicated to owners and other stakeholders. Let's first try to define what is structural health monitoring. Structural health monitoring is maybe about monitoring bridges. This means that you install a lot of sensors on a structure, measure it, and try to understand what is happening on that bridge. For others, structural health monitoring might be about ensuring the safety, for example, of a dam, again to make sure that nothing unforeseen happens to the dam and it can be operated safely. In the case of geotechnical applications, structural health monitoring could be used to reduce risks in excavation. So that's another use of structural health monitoring. If we're talking about pipelines, structural health monitoring can be used to avoid leakages and damage that can result from such leaks. And if we're talking about building, maybe adding a structural monitoring system can also add prestige to a building so that its perceived value can also increase. If we instrument a ship, for example, a tanker, then structural monitoring could be a tool to preserve natural resources and to avoid ecological disasters. Structural monitoring is also a tool to enable remote management of structures, so that from a distance and by connecting to it, the owner or the engineer can manage and understand what is happening in the tunnel, for example. In general, we can say that structural health monitoring is about all of this and even more. It has evolved from being basically a research topic that was developed in universities and research center to a true industry where several companies are active worldwide in supplying, installing, managing, and analyzing data from structural health monitoring systems. And if we think about it, an industry is defined as a meeting place between supply and demand, and so basically between a cost and a perceived benefit. If someone is ready to pay something, it means that he also perceives a benefit in return from what he has bought. So now we should really start and define cost and perceived benefit in the case of structural health monitoring. So this presentation is really about defining first the cost and then the benefits, looking at it from a customer-supplier relationship perspective. This presentation does not contain any sophisticated financial models or even a universal recipe for commercial success, but is just a personal observation derived from practice in many different projects. Okay, so let's get started. The first topic we should tackle is the definition of the cost of a structural health monitoring system. And I define the cost as the sum of the capital investment plus the operational cost. So capital investment is the expenditure which is needed to implement the structural monitoring system, and the operational costs are those recurring costs that are needed to operate it and benefit from it. Capital investment includes several different aspects. Initially, it concerns mostly the design of the system, integration with the structure itself, planning and project management. And once the system is planned and approved, then you need to install the hardware, such as sensor, cables, data acquisition management, and hardware, communication devices, etc. And then those components need to be installed, so there are costs associated with integrating the installation with the building schedule, configuration, commissioning, and reporting about the system installation. Then we come to operational costs. So once the system is installed, then the system needs to be maintained. In some cases, there are spare parts and consumable that needs to be renewed on a regular basis. And then there are costs associated with supplying energy and data communication from and to the system. Other important operational costs are related to the management of the data, publishing the data, archiving the data, making sure that no data gets lost, and last but not least, data analysis costs. So this is very important because only when the data is properly analyzed and interpreted and reported to the people that can make use of this information, then a structural monitoring system can be successful and really useful for the owners. In many projects that we've carried out in the past, we see that the typical cost or investment for a structural monitoring system lies between 0.5% and 3% of the new construction cost. And the hardware cost, so sensors, cables, and data acquisition unit, typically represents less than 50% of the total cost. So the other are more service costs, including installation, maintenance, data analysis, reporting, etc. So really understanding what is the total investment plus the recurring cost is very important for the owner. So before a project is started, everybody needs to understand what will be the cost involved and what costs need to be maintained in the long term to make the system beneficial. Otherwise, maybe the project would get partial funding and be unsuccessful because there's no money left for data management or maintenance, etc. Now that we have defined the cost, we can start identifying the benefits of installing such a system. And I will subdivide those possible benefits into two broad categories: hard benefits and soft benefits. The hard benefits are those that can be quantified in dollars or Swiss francs or euros, so that you can show apple-to-apple comparison between the cost and some savings that are possible thanks to the system. On the other hand, there are soft benefits that are also perceived by the owner or the user of the system, but are more difficult to quantify in financial value. So these will be defined as soft benefits. So let's start and have a look at what those benefits can be. The first benefit is the capital value of the structural monitoring system itself. Since it has an intrinsic value, that can also be perceived as a hard benefit, but this is not very interesting for the owner. Just having something expensive added to the bridge doesn't really add any true value to the structure itself. The second important benefit is related to the reduction of risk. And this is at the same time a hard benefit and a soft benefit. It can be a hard benefit if, for example, a reduction of risk corresponds to a reduction of insurance cost or other upfront cost of the owner. But can also be a reduction of soft benefit, for example, by reducing the risk of damaging the image of a company or other similar indirect damages. An example of a project where such a benefit was realized is the detection of cracks in a tunnel. So in this case, the owner was afraid that cracks would develop in the tunnel lining, and indeed some cracks had appeared before installing the system. So it was decided to install a distributed fiber optic deformation sensor to localize and identify cracks so that remedial action could be taken immediately if such a crack would appear. The approximate cost for this project was 800,000 euros, and the main benefit perceived by the owner was risk reduction. In all the examples that I will give you here, the cost is the total cost, including installation, operation, etc., and in many cases is an estimation, because we don't always have all the information about the indirect cost in installing and operating the system. So here's a scheme of the system that was installed. 5 lines of distributed sensors with a total length of 3 kilometers each are connected to a dye test reading unit, and this allows, as I mentioned, to localize and detect the onset of new cracks in the tunnel and avoid any risk to the trains that use that tunnel. The next benefit I'd like to discuss is increase of safety. That again is a combination of hard benefit and soft benefits. An example of using structural monitoring to achieve that benefit is a project in Kansas where a sinkhole have formed in the past, and those sinkhole can affect train lines, as it's possible to see in this picture, nearby constructions, roads, etc. So in this case, for an approximate cost of $400,000 US, the owner achieved a reduction of risk, insurance, and an increase in the safety of the rail line crossing that area. The cable was installed by a trenching machine that cut a trench in the ground. The cable was then buried in the ground so that any early movement that could point to the formation of a sinkhole can be recorded and localized, so that again traffic can be stopped if it's close to a railway line, or other actions can be taken. The system is fully automatic, and the owner and engineers have an overview of the whole area, and in this case the green line indicates that no significant strain has been detected anyway along the length of the cable, and in case movement is detected, then that area would turn red and alerts would be set off, so that the people in charge are immediately notified. Another possible benefit of implementing an SHM system is an increase of quality in the construction of the structure itself. Again, a hard and soft benefit simultaneously. It is well known that when a process is controlled and measured, the quality improves, because human beings tend to be more careful when they know somebody is watching or checking, and so just by implementing a system to verify the construction quality can increase the quality of the construction. An example of obtaining such a benefit is a project in Singapore, where hundreds of high-rise buildings have been instrumented with SOFO fiber optic sensors for a cost of approximately $25,000 per building. Those sensors are measured on a regular basis during construction, and then during the whole lifetime of the structure. And if a special event happens, such as a tremor or another unforeseen occurrence, then additional measurement can be taken to verify that nothing happened to the structure. But one of the main benefits is to verify the construction process itself and make sure that the building that is constructed corresponds to the building that was designed. In this case, sensors are embedded in column, either precast or cast in place, and then through a junction box, measurement can be taken on a regular basis by connecting a SOFO reading unit to each sensor. On the picture here you can see an example of a measurement being performed, and the graph shows an example of measurements of the column deformation as a function of time. And as you can see, the top line represents a sensor that is basically an outlier. In this case, a column that is loaded much less than the other ones. It turned out that that column was really over-designed for that particular building because some area of the building were not used, and so the load on the column was less than expected. There have been also cases where small settlements have been detected or other deviation from the expected behavior. A further benefit of SHM is the possibility to discover structural reserves in a structure. So sometimes existing structures are in better shape or offer more load carrying capacity than can be expected from the original calculation or visual inspection. So discovering this hidden structural reserve can represent a benefit because the structure, for example a bridge, can be used further, maybe without replacement or strengthening, because the original uncertainties associated with the construction can be resolved by taking measurements. For example, if during the design phase you have to assume the worst possible quality of concrete and the worst possible settlements in the foundations, once the structure is constructed, you can measure the real values of those parameters, and when you redo the calculation, you often find additional structural reserves thanks to the reduction of the uncertainty about the real properties of the structures. An example of such an application was a project we did on an arena in Halifax, Canada. In this case, the owner was worried about the combination of load on the roof generated by a combination of snow and loads hanging in the roof inside, in particular during concerts when lighting and audio equipment is attached to the roof itself. In this case, the total cost of the project was approximately $250,000. And the benefit is that the monitoring campaign proved that no strengthening was needed for that roof, so that much larger cost could be avoided. The arena is used for different purposes, for hockey games, as you can see in this picture, and also for concerts, as it's possible to be seen in this case. Due to changes in the Canadian regulation about snow load on roof, the original calculation of the load carrying capacity of the roof would not allow to hang lighting and other concert material at the same time when snow could be expected on the roof, and this would have been a problem, of course, for the owners. So what was proposed in this case was to install fiber optic sensors on some members of the truss that make the roof, and those members were selected by a finite element analysis as those that would be mostly loaded, and at the same time with a laser distance meter deflections of the roof were measured. And these measurements were performed during heavy snow loads and during concerts to make sure that those strains and those deflections would remain within the limits that were calculated. So basically the worst case scenario that could happen in that building was a combination of a rock concert and a snowfall at the same time. And this is exactly what happened and is shown in this picture here. Basically, here you can see the recorded strains during 2 snowfalls and freezing rain and 2 concerts, one from Ozzy Osbourne and the other from Michael Bublé. And as you can see, in the worst possible combination was during this snow event combined with the Ozzy Osbourne show. We're probably the only one having used Ozzy Osbourne as a loading device, and but this project was very successful because the recorded strains were much lower than the critical strains, and so it was possible to demonstrate that the arena could operate safely within the new code limits without any strengthening. Another opposite benefit is the early detection of defects. So we have seen before that many structures are in better shape than expected, but there are also a few that might have hidden problems, and it's important to detect those problems early on in the structure life so that they can be corrected. An example is a project we carried out on a bridge in Switzerland where a new traffic lane was added on one side of the bridge, and the owner wanted to make sure that the design assumptions were respected and no defects were introduced by the new construction. In particular, it was the new part of the bridge was designed to act monolithically with the existing part of the bridge, and so it was important to make sure that this connection was really good between the old concrete and the new concrete. An example of those results is shown in the graph here, where the onset of cracks could be identified just a few days after pouring, while the formwork was still around the concrete, and so the contractor could adjust the concrete mixture to avoid those cracks in the next pours. So those original defects could be identified and corrected early on. On the bottom graph you can see a comparison of sensors installed in the old concrete and in the new concrete, and the fact that the two curves superimpose exactly showed that a very good cohesion between the two materials could be achieved. So that was a proof of the quality of the construction in this case. Another benefit that can be achieved is the safe lifetime extension of structures, and this is a hard benefit because real money can be saved. In this case, the idea is to apply structural health monitoring techniques on structures that are candidates for replacement. For example, imagine that you have a number of bridges, let's say 10 bridges, that after visual inspection, maybe some superficial analysis, show that they are structurally deficient and should be replaced because, for example, they can no longer hold the traffic, or the material have degraded in a significant way. And let's assume that replacing those 10 bridges would cost 100%, let's say, for example, 100 million euros. Now imagine that instead of replacing those bridges, you first carry out a structural health monitoring project that costs about 3% of that replacement cost. And this would include installing sensor, taking reading, and comparing those readings with the finite element model, and updating the model so that you have a better idea if the bridge really needs replacement or not. After carrying out that analysis, we can imagine that 20% of the bridges are found to be okay. So this is quite conservative. We just assume that out of the 10 bridges, 2 are actually in much better shape than was originally expected. In reality, I think that number would be higher from our experience. We also assume that another 20% of the bridges are found to be in, let's say, average shape and need some rehabilitation, but do not need a complete replacement. And we can also assume that the rehabilitation cost is about 30%, for example, of the replacement cost. And finally, we assume that 60% of the bridges are really found to be in a bad condition and really need replacement. So if we now calculate the cost of that strategy, we see that we have a 3% cost for implementing the SHM system, 20% of the bridges that have 30% of the cost. These are the rehabilitated ones, plus 60% of the bridges that have 100% of the cost. These are the bridge that needs a replacement. And when you calculate the total cost, it comes out at 69% compared to the 100% cost of replacing the bridges immediately. So that corresponds to a saving of 31%, and this is real money that can be saved without any compromise on the security of the structures themselves. An example of the safe lifetime extension of a bridge is the Göta Bridge in Göteborg, Sweden. This bridge is relatively old and made of steel, and in the past some fatigue cracks have appeared on the girders, so that the owner was afraid that other cracks would appear and jeopardize the security or the stability of the bridge. For a cost which was relatively high, at around 1 million euros, it was possible to postpone the replacement of the bridge by several years, and so that corresponded to a big saving for direct cost of rebuilding the bridge, but also indirect cost that would have been created by for example, the unavailability of the structure during the reconstruction. In this case, distributed fiber optic sensors were installed on several girders along the wall length of the bridge itself, so that any new crack that would appear on the steel girders would be detected and localized, and immediate action like repair or stopping the traffic on the bridge could be carried out. Another possible benefit of structural health monitoring, a soft benefit in this case, is the increase of knowledge. That can be both scientific knowledge, and this would, for example, benefit a university or another research center, but could also be a knowledge that can be used by an engineer or an owner and be applied on similar structures that are built or repaired in the future. An example of such an application is this full-scale test of a shaft that was carried out in California to make sure that this shaft would perform correctly in the case of an earthquake. In this case, for an approximate cost of $200,000, it was possible to carry out a full-scale simulation. In this case, the benefits are indirect, like scientific publication or receiving grants to carry out the research itself. In other cases, applying a structural monitoring system is required to adhere to standards and regulations. For example, in the case of nuclear power plants or large dams, it is required by law to install a structural health monitoring system. For example, in this project in Finland, where a combination of fiber optic sensors and traditional sensor were installed, it's possible to demonstrate the safety and to comply to the safety regulation of the local and international organizations. Another benefit can be related to the image, the prestige, and the public perception about projects. This is, of course, a soft benefit. In this case, we are looking at a way of increasing the quality, not only of the structure itself, but also the quality of the perception of the public of that structure. An example of that is the instrumentation of the new I-35 West Bridge in Minneapolis. This is the bridge that replaces the infamous bridge that collapsed, killing several people a few years ago. And when rebuilding the bridge, it was of course important to make it safe and durable, but it was also important to restore the confidence of the people in using the new bridge. So in this case, for a cost of approximately $500,000, a comprehensive structural monitoring system was installed to help during the construction and to provide long-term data for research purposes. But one of the main reasons was really to communicate to the public that this new bridge would not have the same fate as the original one. Here you can see a schematic layout of the different sensors that were installed in the bridge, a total of 323 sensors, including vibrating wire strain gauges, temperature sensor, a displacement sensor, accelerometers, corrosion sensor, and fiber optic long gauge sensor were installed in the bridge. Here you see an example of data that was obtained during a load test performed on the bridge. As you can see, a lot of trucks were needed to properly load the bridge, and on the bottom you can see the response to temperature, which is the general trend, and the jumps correspond to different load scenarios that were carried out on the bridge. Again, to check if the response would match the original design of the bridge. Now that we have seen the many possible benefits that are associated with an SHM system, I would like to spend a few minutes to discuss how it's possible to design an SHM system that maximizes the owner's benefit, so that the cost-benefit ratio can also be optimized. Over the years, we have developed this 7-step SHM methodology, which allows the creation of an optimal SHM system for the available budget and to maximize the benefit for the owner. First step consists in identifying the structure that needs or benefits from monitoring. Second step, acquire information on probable risks and opportunity, working together with design engineers and owners. Step number 3 is establish expected responses to those risks and opportunities. Step number 4, designing an SHM system to detect responses and select the appropriate sensors. Number 5, install and calibrate the system. Number 6, acquire and manage data. And number 7, assess the field data. So let's have a look at each of these steps in more detail. When identifying which structure can benefit from SHM, there is of course a large variety, but we've seen that structure that include innovative aspects, structure that are unusual, that have unusual associated risk or uncertainties, such as geological conditions, seismic risk, meteorological risk like risk of typhoon, aggressive environment, or some vulnerability during construction. Those structures can benefit in particular from SHM. Also structures that are critical at a network level. For example, if they are closed, they would generate significant disturbance to the traffic. Or maybe a structure which is similar to many other similar structures, so that data from that system can be applied to other structures. As we have seen, also existing structure with known deficiency or low ratings, as well as replacement as candidates for replacement or major refurbishment work. Once a specific structure has been identified, then the SHM system designer must work together with the engineer who has designed the structure and the owner to identify what risks and what opportunities are associated with a specific structure. An example of risk would be corrosion, settlements, damage from earthquake. An example of opportunity would be residual or additional load carrying capacity, or better condition than expected, or stiffer structure than calculated from finite element analysis. So this analysis will lead to a list of possible events and degradation that can affect the structure, and also they can be ranked by impact and probability, so that it's possible to concentrate on those risks and opportunities that have a higher probability and a higher impact. For each of those risks and opportunities, it is also important to identify what would be the associated response. So what can be observed directly or indirectly that would indicate that that risk has materialized. For example, in the case of corrosion, you can detect a change in the electrochemical properties, or in the case of a settlement, you can detect a deformation or a redistribution of loads among columns. And at this stage, we can also roughly quantify the expected responses, so that when we select the sensor, we will select sensor with the correct range and accuracy. Also, some risks maybe are more probable at specific locations, so we can identify those locations. And also we can define which risks are better addressed by SHM and which are better addressed by an inspection program. Now we come to step number 4, where we select the appropriate sensors and technology, considering also the lifetime of an SHM system. So if it's only useful during construction, maybe you can use sensors that are not as durable as those that you would select for a long-term dam monitoring project where the sensor is buried and can never be replaced. This is also the time to consider the available budget. Since we have ranked the risks, basically we can go through one risk at a time, and when the budget is consumed, we know that we have addressed the most important risks that we can afford. This is also the right moment to consider reliability and redundancy. So if some sensors are very critical, it's important maybe to double them or to have two different measurements leading to detecting the same risk. And planning for installation and schedule can also be started. It's important to point out that this is only step number 4, and in some projects in the past people have started at this point. So because one technology was available, there was an interest in applying it without really thinking if that was the right tool to address the concerns of the owner. So if you don't define the question, you cannot really start proposing an answer. Step number 5 includes installation and testing of all components according to the specification and the manufacturer manuals. And this phase usually concludes with a site acceptance test where all systems are tested and handed over to those people that will operate the system. Step number 6, data acquisition and management. We recommend using a database system so that data can be preserved over the long term and people are able to make sense of the measurement even in 20 years. Data can also be distributed to those people that need to access it. And at the same time as we record the data, we also have to document interventions and other things that happen in the lifetime of the structure and in the lifetime of the SHM system itself. Finally, we come to the step that really creates value, is the data assessment. And it is very important that the raw data is transformed into useful information by analyzing the response of the structure. If you have gone through the previous steps, this will be easier because we already know what to expect, and we also know what is the possible risk that can create that type of measurement that are being observed. It's also important to establish procedure to respond to the detection of a risk or a degradation, and this must be done beforehand so that, for example, if a new crack is detected, we know what to do. Should we just write a report, or should we stop the traffic immediately, or should we send an inspector to confirm that, so that when these cases arise, everybody is on the same page on what needs to be done. In some cases, analyzing the data might prompt needs for further investigation, including inspection, testing, or adding new sensors to make sense of the measurement. In some cases, data assessment can also be performed automatically, generating alerts when predefined thresholds are reached, or also generate periodic reports, including statistical analysis on the data, etc. Now that we have analyzed the benefits and the cost and the way to implement this system, one could ask, what are the retaining forces? Why, if we can demonstrate in so many cases a benefit of using an SHM system, SHM system still remain relatively rare, and it's not a standard practice to use them for new construction or for structure needing repairs, etc. So in the final part of my presentation, I would like to examine a few of the retaining forces so that maybe you can recognize them when you will see them in the future. The main things that limit SHM is, on one side, difficulty to estimate the cost and benefit. So when the owner must consider installing an SHM system or not, sometimes it's difficult for him to really understand how much the system and its operation will cost and what will be the benefit that he obtains. So it's very important to communicate transparently those two parameters. Another limiting factor is sometimes the large number of actors that are needed to carry out an SHM project. You need a supplier of sensors, you need someone to install it, you need someone to analyze it, etc. So we have introduced, for example, the SHM Live concept to reunite all these actors under a single, let's say, coordinator, so that there is only one interface to the owner. Also, some owners don't have the experience or the people to manage SHM projects, so they see it as a distraction, and maybe in those cases it's appropriate to outsource those work to companies that can do that. Another limitation is that most owners need actionable information and not raw data. So it's very important to provide data in a way that is useful to the owner and not in a way which is appealing to the sensor supplier. And finally, limited budget are, of course, a limitation to the use of SHM. There are, however, other limitations. The first limitation, what I would call our #1 competitor, is basically doing nothing. In so many cases, the cost and benefit of implementing a structural monitoring system is compared to the cost of doing nothing. And of course, doing nothing is a competitor you can never beat on price. So it's only by demonstrating the benefits of implementing such a system that you can convince the owner that it's better to do something than to do nothing. Our second major competitor, I summarize it with the phrase fixing potholes. In many cases, when budgets are available, the politician and the owners prefer to fix things that are immediately visible to the users and not necessarily invest in the long-term value or quality or sustainability of a network of structures. So this can divert money from, let's say, a long-term valuable investment to something that is maybe just a band-aid, but as an immediate return of image on those implementing it. The third main competitor that we have is keep doing what you always did. Structural monitoring is relatively recent in some fields. It's very established in other, like dams or nuclear power plants. But for bridges, many owners are more confident in continuing their way of managing structures and security, and adopting something new is perceived as a risk, maybe of doing something wrong or trying something that will not work. So, in summary, I didn't promise a universal recipe for commercial success in structural monitoring, but maybe there is a couple of recommendations that I can use as conclusion of this presentation. As with any other business, understanding and satisfying the end user needs and identifying his benefit is crucial to make sure that you are successful in your business. One phrase I always remember is that a good designer has 2 ears but only one mouth. So it's very important that we listen to the customers, to the owner, to engineers, and understand what are their real questions, because we can provide answers only once we understand the questions. And finally, a good recommendation for marketing any technology or service is that the bait must be appealing to the fish and not necessarily to the fisherman. And with that, I would like to conclude my presentation, and thank you for your attention. As usual, you can ask questions using the chat window, which is on the right-hand side of your screen, and I'll be happy to answer your question in that way or by email in the future. Thank you very much for your attention. Bye-bye.